visiting this class is that people actually use the computers in the room. I had no idea. I didn't even know how to log into that thing. Anyway, so this afternoon is going to be a work session. So I don't know how you guys usually do worksheets, but that's what happens when another prof just parachutes into a class for a couple days. They do things a little differently. But yeah, we're going to go through a couple worksheets questions with you, and we're going to present you the problem, and then you're going to get out your pen and paper, your iPad, your crow with ink on its beak, whatever you want, and work on the question. Sit there and think about it. Talk to your neighbor about it. You know, problems are meant to be solved collaboratively. We'll walk around. We'll give you some tips. We'll help you get unstuck, and then we'll work through the solution with you. And we hope to get through about 3 or 4 questions this way today. Okay? And like I said, last lecture was very much about visually, intuitively, what's going on with constructing features. This is more about like just the basics. How do we think about functions? Because ultimately that's what we're working with, right? And how do the concepts in the visualizations start to map onto just basic math, right? So with that, I'm going to turn it over to our awesome TA here, and he's going to propose the question, and then we're going to start working on it together.
Okay. So we have two functions. This is v of s equal to minus s square, and v of s equal to 1 minus half of s. So the idea is s represents the state, and in this case, state is just a real number, and v of s. So this is like v pi. You can imagine that it's v pi of s. So the true value function in one case looks like this, in another case it looks like this. Okay. The question is, can you design features for each of these functions separately so that you can approximate them as a linear function of these features? And then can you also design features that make this approximation exact? So for instance, one feature could be 1. Just have a feature that's always 1. That can approximate these functions in a linear way, but maybe that approximation is bad. So design good features. And the second question is, can you design one single set of features that allows you to represent both these functions? Okay.
we want to make this inner product look like this red line, right? And so we know the state space X is this real line. So how can we bend the real line to look like the red line? Okay. So I'm just going to give you a couple more tips, and then we're going to solve the first one, and then get you to think about the second one again. And if you're ahead, you can just look at the next problems. That's perfectly fine. In fact, if you're ahead, you can just start working on problem 2, because it'll just, no matter how smart you are, it'll just be annoying to write out. Anyway, let's think about this. Let's think about 2 places here, -2 and +2. Okay, and let me tell you that W, we're going to say W is equal to -1. So what does that immediately tell me about the size of my feature vector? It's one-dimensional, right? So we know this mapping from S is going to be one thing, right? Okay, now we can think about what could x of s be that when you multiply by -1 gives us this value at -2 and 2. So let's just do the solution of this one, and then we'll get to think about the second one, and then we'll move on. Okay.
So for the first one, the solution can be x of s is s squared.
Okay, so for anyone, is that like a category error? Like, what on earth are you talking about? Makes sense, right? We're just trying to multiply that -1 by s squared, and then we get the function minus s squared, right? Notice we have this cube s squared function, and we're getting
Hello, can you hear me now, online people? Okay, let's call this x1. So first part, for x2, one answer could be this. So the feature vector is a vector of size 2, and it maps the state S to a vector which has an element which is always 1 and another which is S. So the first element is the bias, if you have heard that terminology. Okay, and can you design features to make the approximation exact? Yes. Yes, Adam. Okay, what's W in the second example? Sorry. Okay. Okay, yeah. So as our friend said, W is this 1 and minus half. Oh, by the way, if we didn't have this, can you make this approximation exact? Then one a completely valid answer is this. Like excess is 0. Okay, but you can't make the approximation exact with this. And can you design one set of features that allow you to represent both the functions? Then you can just combine them. So x3 would be 1 s and s squared. Make sense? Okay. Let's move on to the next one. Okay. 3. We'll go to question 3. Okay. So now in this problem, the state space is discrete, and the states are the numbers 0, 0.01, and up to 1. So we have 101 different numbers which are which represent our states. Okay. Now we assume that the true value function is given by this equation or this graph. So the value of a state which is 1 would be 2. Okay, so we have the true value function. Now we decide to create features with state aggregation and choose to aggregate the states into 2 bins. Actually, ignore this first, sorry. Okay, we aggregate the states into 2 bins. So this is bin 1 and this is bin 2. So any state which lies here would be considered as one state. So it's like you're trying to see something and either you see darkness or you see light. You don't see anything else. You're aggregating the states. And this means that the value function, it will learn a single number W1 for all the states that lie here and W2 for all the states that lie here. Okay. So now your question is, okay, you approximated your value function using state aggregation. Now the question is, can you do this? Can you achieve this same approximation using a linear value function? And then decide the features that allow you to do so. So you have a value function which works in this using state aggregation, and now the question asks you to come up with features which allows you to get the same value function approximation using linear functions. Okay. Second question is, you minimize the mean squared value error, which is defined by this equation, and D is the uniform weighting. So you have 101 states, so D is just 1 over 101. And then the question is, how do you minimize this? Find the weight vector which minimizes this. So find W star which minimizes mean squared value error. And the final question is, it gives you a specific weighting. So the final question tells you that, okay, now the weighting is D of S is 0 for anything outside this range. So D of S is uniform here and 0 everywhere else. Then what W star minimizes your mean squared value error?
So do we all remember what two-bin state aggregation would mean in this problem? Would it be a good state aggregation in this problem? Yeah? But if we want to represent this function, is it a good representation of the function? I'm thinking no, right? It's very, very coarse. So remember when we did the 1,000-state chain and we said we're going to have groups of 10 states, or maybe it was 100. I don't remember. It was groups of states, right? Well, this is kind of that, except in the extreme. We're going to have one number to represent the function on this side and one number to represent the function on the other side, right? So it's a pretty coarse approximation. So, sometimes when we see these things, they can be abstract. So you can think about, this is kind of like a chain where we had to group all the states on the left side of the chain in one grouping and all the states on the other side of the chain into one grouping, right? And that's how we think about this aggregation. It's trying to summarize, again, our state space along the x-axis and then generate features so that when we do our inner product, we hope it looks something like the red line, but with two numbers, it's not going to be a very good one.
Okay, so essentially what we are trying to do is we are trying to approximate the value function using this. So this is W1 and this is W2. And the first question asks us to create features that can approximate this type of a function. So your features can simply be x of s is say 1 0 for s in 0 to 0.5, and it's 0 1 if your state is in, if your state is in 0.5 and 1. Make sense? So for this region you get this feature, and your approximation would be W1, and for this region it will be W2.
Remember the sanity check here is the state aggregation is safe. Just fine, either indicate. You're either in this aggregation or you're in another aggregation. So it was kind of like a tip implicit in the question that the answer had to be binary. So where is this approximation going to be really good? Where in the state space? There's two places. It's also a hint of solving the next one. So we can say where this approximation is going to be really good, and maybe you guys can use that to think about question 2.
Right.
Maybe the instructor knows. Where's this approximation awesome? What part of the state space?
Okay, from this diagram, if you're using these green values, then it's perfect here and here. It's exactly equal.
So if your agent ends up right at those 2 possible points, you're right on the red line. You're perfect. You're the perfect value function. Everywhere else. Now we can.
Okay, now that we have this nice diagram that I drew, the second question is, how do you find these W1 and W2 such that this green approximation to this true value function, it minimizes the mean squared value error? Okay, oh, Adam told me maybe go for intuition first. Yeah, go ahead.
Also known as, what's the die function? Oh, given this state aggregation, what die function do we find if we solve this? Again, it's not
Right. Okay, any guesses what W1 and W2 would minimize that value error? 1. So you're saying it will be, oh, I have a lot of markers. Okay. So it will be maybe this, right? So your guess is W1 is equal to W2 is equal to 1. Yeah.
For the second W2, I got 1.0. Definitely understand. First, let me explain why it is.
Right.
So because it's squared, the further you are from your edge,
Right.
error will increase. Like
Right.
theoretically, as you get on one side, for any
Right.
thing you get on the other. That is
Yes.
the error that appears on the side. On the left side, we have 51 value, and like the middle of that one is precisely on 25, where it does tell you it's 1. On the other side, we've got 50 value, right? Maybe to the outcome. It's 0.04 and
Right. Right. So what Raina is saying is, oh, by the way, bin 1, it contains 0.5. So the value would be exactly 1. But bin 2, since it does not contain 0.5, its value wouldn't exactly be 1. And it'll be 1.02, 1.02. Makes sense. I think there's also value in writing, pedagogical value in writing MSVE. Should I write that? Okay, I'll write this. So this would be, now we'll split our sums across the two bins. So first sum, S is in 0 to 0.5. And then second sum, S is in 0.5 to 1. Okay. Now what is my value function here? My value function here would be, right, 2, it's 2 minus 4s. I think it's this. And what is my approximation? State aggregation. What is my approximation here? W1. And here, my value function is this, and my approximation is W2. And you can also just directly minimize this, and you'll obtain these values. Now just go on to the third part. Okay, third part is super similar. You can just modify this and
The third part is just getting you to think about the role of the state weighting, right? Remember the state weighting was us specifying which states we care about getting the error low in, right? And so the third part is saying, imagine if we don't care about getting the error right for this part of the function. We're only concerned with this part of the function, the state space from 1 to 0.25. How would that change our solution? So you can work through that and we can release those calculations, but it's just really thinking about how this thing impacts your solution, right? If you have a way to communicate to your agent, don't worry about knitting underwater. Never matters to knit underwater. Your agent won't learn about it, okay? So that's the point of that part.
Okay, let's move on to fourth question. Okay, so we are given an update rule with the target UT, and this is the update rule. Assume that we are using linear function approximation to represent our value function. So value function is the inner product between some features and your weight vector. The question is, what happens to this update? So this update, what happens to this update when you study these features, x tilde of s, which is just double the old features? So will this pose any problem? And if it will, then why? If it does not pose any problem, then why not? And the second part is, so you might have seen in the book that the book recommends using this step size for tile coding. It's a very basic question. It's just telling you, okay, we have a tile coding scheme where we are using 10 tiles, 10 tilings, and then tau is 1000. Then what is alpha?
So one tip for thinking about this question is just think about our update rule and just plug some of these things in, right? So we're doing linear function approximation. So this can be plugged into here, right? And then again, linear function approximation. So what is this part? What does this become? The gradient of our value function. We'll worry about the twice in a second, but it's just the feature vector, right? So we have the feature vector here, and we have the inner product between the weight vector times the feature vector. And now in addition, we're saying, Oh, now imagine the situation where our feature vector has a 2 in front of it. So now we can literally just think about how many 2's are going to be in our update now? 2, right? So things will get bigger, right? When we do an update, the update will be how much larger? Give me an integer between 4 and 4, right? It'll be 4 times larger. So what should we do about that? Imagine we had started with the feature vector that wasn't 2 times larger. And you were solving a problem, you were using one of the notebooks on Coursera, and you were fiddling with the step size until, the value function was really, really nice. Converge to a beautiful value function. Maybe your step size was 0.025 or something, right? And then I said, aha, in the next cell in the notebook, we're going to double the feature vector. What would you have to do to make it so that when you ran it again, your value function would converge to that beautiful place?
Just need another constant that offsets the constant that you should.
So what could we change about our learning algorithm? Make the step size smaller, right? By 4. And so this is just motivating this general rule of thumb that's in the textbook, which is it matters how big your feature vector is for picking your step size. Now, all the cool people would tell you, don't worry about it. Adam, not me, the other Adam, even though there's another optimizer called Adam W. My name's Adam White. It's very weird. Anyway, they just say, set it to 10 to the minus 3 and use Adam. And of course, that does have normalization inside of it, the space and the scale of things. And so that's also related to this idea that how big your features are should be related to how you set your step size. We're over time by 1 minute. You guys have been 1 minute extra patient. I very much appreciate that. And we'll see you all on Monday.